let's begin today. So give me the geometric interpretation of what you've just done. Someone have an idea of like what is it we just did? Clearly L of x, I mean, all these symbols could mean anything you like, but of course L of x equals that thing. It reminds us of what thing we've just recently done. Yeah, that's the linearization of, in the most generic form possible that we could have written it. And so what am I asking you to do when I ask you to solve L of x equals 0? Yeah, where the linearization, where that line, or the tangent line, hits the x-axis, yes, right? All right, so interesting. We'll talk about why that might be useful in just a second. So, anything else? Any comments from the class before we discuss Newton's method? Keep in mind that our unit is still about the applications we might have for derivatives. So we've seen lots of them. Here's another one. Here's another useful thing we can do with just a little derivative technology, and really with this neat observation we've been making that, like, you know, in calculus our move keeps, it seems like our move is always like, let's pretend something's a line, right? So that suggests maybe a way in on a problem that people have had down through the years. You don't maybe think of it very much anymore because finding zeros is something that you usually let your calculator do. But Newton's method maybe shows you what's under the hood of your calculator. You maybe have never stopped to wonder, like, how does your calculator actually approximate a zero? And before you leave today, you're going to know. Okay. It's named, of course, for Isaac Newton. Sometimes it's also called the Newton-Raphson method. I don't know who that guy is, but whatever. So, yeah, I just threw him under the bus. I mean, I don't know. I'm sure Newton was not the only one to to discover this on his own. It's really, once you hear it today, it's quite simple, really. Again, emphasis on the fact that, like, you usually use your calculator to do this, but Newton's method will describe a method for finding a root arbitrarily close to the actual value as possible, if you like. Yes, sir?
Can we just, like, take the quadratic formula?
Yeah, if you have a quadratic. I mean, to be fair, the first example I'm going to give you is a quadratic, which you don't even need a quadratic formula for on this one. You don't have to. I mean, we could just say what the root is off the top of our head right now, if you like. But in general, so this will be good. Our first example is one that we do know how to find the root using another method. But I'm talking about any function. Like, you realize that your calculator is able to find, if you've played around with your calculator before, and even for the most terrible functions, you know, whatever, find the roots of, you know, e to the 3x times sine x or something like that. Like, you have no way of algebraically obtaining those solutions. And even for higher order polynomial functions, we don't have a way of doing anything. In fact, it's provably true, I don't know if someone's ever discussed this with you, it's actually provably true that there are no methods for solving polynomials of degree 5 or higher with exact solutions. There's just no way to do it. So the only thing we can do for the general function we run across in the woods, like the only way we can find solutions is by approximation. So actually the garden variety function is not one that you know how to use algebraic techniques to solve. So let's actually demonstrate how this technique works with this function, with one which you already know how to find the zeros of another way. And we'll use Newton's method to show you, just with this little cute example, how it works. Okay. So we're going to try and get this zero right here using this new method. And the method starts by using a guess. I've written the derivative down for you, but we'll tell you why that's useful in a second here. So let's start with a guess that's not that great, but we'll start with a guess of 3, okay? And already you're kind of thinking, this does sound familiar. This does sound like what my calculator makes me do, doesn't it? When you ask for a 0 or asks for a guess. So it needs like a seed. You need a seed for this algorithm, okay? So that's our seed. Our first guess is 3, and then this should look this is how bad we were, right? If 3 was the perfect guess, we would have gotten what here? 0, right? Like that, but that didn't happen. So we got 1.5 for the y value instead. And then, I don't know how to solve polynomial equations, but I am all about finding the zeros of linear equations. So let's assume that this is the function we're working with. And what is that? That's the tangent line there. I think the slope is just, it happens to be 3 here because f prime is just x. So that's convenient for this first example. So the slope of that line is 3. So do you think you could figure out, I don't know, what this value is right here? I think you could. If the slope of this line is 3, let's call this distance we're looking for z. And this is 1.5. It's the y-coordinate. What is this distance here? Well, should be 1.5 over z is the slope, 3 of the tangent line, right? 1.5 over z is equal to the slope, which we just calculated to be 3. So therefore z, this distance here, must be 1.5 over 3. And what this provides is a better, if we subtract this off of here, right? That is 3 minus this distance we just computed. What this provides is a better approximation of the 0. .5 is a better guess. But now that just makes you want to do what? Still not the 0 of this function. What does it make you want to do? Well, maybe it makes us want to run this process again with a better guess, right? So 2.5 is right now our best guess for this. We started with 3, but by using this linearization along here, we found a better guess for the 0. By the way, does this look familiar at all? Let's just start decomposing what we just did. In general, what was this 3? This is a little confusing, actually. Maybe this was a bad first example. This 3 was what? That was the first guess, yeah. And then what was this 1.5? That was f of 3. Agree?
Yeah.
And what was this 3? Careful, because it's not that 3, I promise. Like where we got that. That was f prime of 3. So just to say it again, this was f of 3, excuse me, the first guess, x0 we might call it, minus f prime of 3, f of 3 divided by f prime of 3, right? All right, so our new guess is 2.5. Well, oh yeah, sorry, I have that all highlighted here. Probably the things we just said. Yay, it's so exciting. Okay. So our new guess is 2.5, and guess what this slide's going to look like? Same as the last, except now with a new guess of 2.5. Now we're here, right? Now, of course, 2.5 is not the perfect answer, because if we put 2.5 into the function, then we should have gotten 0, but we didn't. We got 0.125, but that's better change than we got before. We got a lot of extra change last time when we plugged in 3. But now 2.5, it's not too bad. You know, it's close to 0, the answer we're getting out of this function. So let's repeat. I honestly have nothing new to say except to just repeat this calculation, right? So I found that the tangent line here at this particular point has a slope of 2.5. So again, we're going to figure out what this distance here is, this z distance here. And we're going to subtract that from 2.5. 2.5 is our current guess. So what is this distance here that we're going to have to subtract off? Again, it's 0.125 over 2.5. You can skate over the details a little bit there again, but that's that distance. So we're going to subtract that off, and we get an even better guess. I can see the hunger in your eyes. You'd like to do it again, wouldn't you?
Yes.
Yeah.
Yes.
2.45 is a very good approximation, but can we do better? Yeah. Yeah, go ahead. Sorry. Yeah, this is the guess we've had. Yeah, so we start with the guess, and then this is like our adjustment to to generate our new guess, right? This is our guess, and this is the amount that we were off by, right? This piece here. This one is the slope, which again, it's unfortunate on this particular one. Maybe I shouldn't have done this. The slope The slope happens to be the same there, right? The derivative is x. In general, these will not be necessarily the same, no. Right. Why do you put the y over the slope? Okay, let's go back to the previous slide because I have it there. So do you agree that, do you know the slope of this line? I think it's 3, right? We calculated it. We can calculate it using the derivative. And then do you know this, the rise? Well, the only thing you don't know is the run, right? So, or you can refer to Marcus's warm-up too to show that that 0 right there, if you solve for it, is in fact the previous guess minus the function over the derivative of the value at that point. So we're doing this another time. 2.45. Let's do it one more time. Look how good we are getting, right? If you plug this into your original function, it's not 0, but it's also not too bad, right? We're getting pretty close to getting a value of actually getting 0. Again, tell me what the derivative is there, and give us a. It's getting a little messy here, but just to keep track of where we are, we started with a guess of of 3. We then improved that to 2.5, and then improved that to 2.45, and now finally we've improved it to this. Okay, and now I know that's 4 different guesses. I would say that we've done this process 3 times, though, wouldn't you? Because the first one was like not really, it was provided for us. We did 1 time, and we got another guess of 2.5. We did it a second time, got a guess of 2.45, and then we did it a third time, and we got this guess, which is really just remarkably good. If you plug this into the function, I'll just tell you right now that you get 0.00000013, etc. Like it's basically as good for any engineering purpose that you might have in life as the real 0. And keep in mind that we only did this little process we just did 3 times, and yet we got a very, very good answer. All right, so this helps you understand why your calculator can give you very, very good answers on these when you do a guess. By the way, what is the actual root? Root 6. Type in root 6 in your calculator. I mean, you can see that this is pretty close to that. But this is probably, I don't know how many decimal places is this accurate to root 6 for. I mean, it's probably 6 or 7 decimal places. Try to type in root 6. We just got a very, very good approximation of it, like root 6. Yeah, John?
So you can use this to estimates for roots as well.
Yeah, and actually we did do that a little bit with just 1 time with the idea of differentials and linearization, right? But this would be us repeating that process over and over again to get even better approximations. Is that cool? You like this? Let's do it again with another one. All right. Well, let me put this in a. We should put this in a box first. Again, this is called Newton's method. I think you know the word recursive. If you were to use the word recursive, I think now would be the time you use it, right? Don't wait. Use the previous result in any recursive. Think about the recursive sequences maybe you thought about maybe in your life before, or any kind of recursive algorithm that you might have used. If you're a computer programmer, then maybe you've thought about recursion more than most people. But this is a little algorithm, and it's a recursive algorithm. And each step, I said the last time we did 3 kind of steps. Did we do it kind of 3 times? We would say that we did 3 iterations of the method, of the algorithm. So, make a guess. In practice, we will, and AP will, provide you with a guess usually, just so that everyone gets the same approximation after a couple steps. But in life, you would probably make some kind of first guess and then refine it. And then step 2 would be to actually, continue using this process using this algorithm right here. We usually call the initial guess x0 because no iterations have happened yet. So in the previous result, x0 would have been 3. That's like before you do any iterations, that was our guess. And then x1, that is the guess we have after doing 1 iteration, was 2.5. And then we did it again, and we got 2.45. And then we did it one last time, but after the third iteration, we got whatever that nonsense was, 2.449 stuff. So this is that process. Each time we use this, I don't know if you felt us doing this, but that's what we were doing, right? Are you comfortable with the subscript notation here? Xn plus 1 equals xn minus, so this is all the previous guess here, xn, xn, xn. And this generates for you the next guess. And all it is, just to be clear again, is what Marcus wrote on the warm-up today, right? Isn't that all it is? X equals, he wrote it not with the n plus 1 and n, but x equals x0 minus f of x0 over f prime of x0. Well, that would just be this first step, going from here to here. So obviously just repeat. Anytime we have like an algorithm that's so systematic, it's so easy to write down, formulate, it does doesn't it just invite us programming a computer to do it for us, right? Yes. Yeah, so that's what we've done, right? Like we'd like to, you know, you code it up, right? You can make your own calculator if you like. Just thought I'd show you another visual on this. Here's another sum function. It's yeah, I think it's I stole this off of a German website.
Ah, that's why it's more cool.
Nice little animation of this happening. Again, calculus, all calculus is us pretending everything is lines, okay? Do you watch this converging here? Notice that sometimes the next guess isn't better. I just want to make sure you're clear on this. Like sometimes it hops around a little bit until it narrows in on it. Let's watch it one more time. There's an initial, now they're calling the initial guess x1. Ignore that because I think that'll confuse young minds. Okay. But whatever, it doesn't matter. It doesn't matter. The point is they're using the process. Look at the line. There it is. Ooh, that's good stuff, right? Anyway. You want to see it again?
Is it a GIF? Dossie's cool. No, it's a GIF.
What? It's a GIF.
Yeah, it's a GIF. No, you're thinking. So it's peanut butter. It's like the graphic.
You can watch this over and over at home later. Okay. All right, let's find where. Notice that this, of course, also explains how your calculator might find the intersection between two curves too. Obviously, those are really one and the same problem, aren't they? Because if I'm asking where this curve crosses y equals 1, then I'm really just asking for the zeros of of that function. Where do I have it? There, right? I'm asking really to solve this equation. That will be sufficient for me. So maybe even though I phrased the question this way, what I'm actually going to do is I'm going to be finding the zeros of this function f I've written down here. And just because I think we'll need it, let's write down what the derivative is. And then I'm actually going to organize my work in a table. You don't have to. If that obscures understanding rather than it helps elucidate it, then don't use it. Do whatever is good for you. Okay. But I just want to kind of keep track of my iterations and the result I get on each one. So again, no iteration here, but my initial guess, I'm going to say is 1. I'm just going to supply you with that, okay? I'm supplying you with the first guess. That's x0. So maybe we can all do this separately too here. What do you get when you plug in? Do you have this, like actually let's pull out our calculators because I'd like you to get good with this method on your calculator here. I want to make sure you're getting the same answers I do. I want to hold your hand this time. So we need to plug in, maybe put this in y1, then you can use your y1 feature on your calculator to hit these each time or however you want to do it. By the way, keep in mind that this is an example of a very, very simple cubic equation that you really don't know how to solve by hand, probably. There is a method, but it's not one we teach in high school. Did you get -1? If you plug 1 into this function right here, I think we can actually even do that without the calculator. We get -1. And we also are going to need, we already know that we're going to need the derivative value at x equals 1 as well. And again, even without a calculator, I think we can do this first step, right? 1 squared is 1 times 3 is 3 minus 1 is 2. Beautiful. And then how do we get the next guess again? Oh yeah, that's right. We take our current guess, 1, and subtract the function at the previous guess divided by the derivative value at the previous guess. So what should that be? It should be 1 minus, or plus, I guess, 1 minus negative 1 over 2, right? So what's our new guess going to be? 1.5. Good. So that goes on the next line of the table. Yeah? Now, after one iteration, we have 1.5 is our new guess. I might call that, like I said, I might call that x1, right? This was x0. This is x1, our guess after only one iteration. All right, then do this again. Now here's where we might need the help of our calculator as it's getting messier, especially in the next line of the table. So plug this into your 1.5 into your function and into your derivative, and then use this little formula. Or you can just do the formula all at once if you like, whatever. Maybe you have the derivative in y2, right? That'd be a cool way to do it.
And then in y3, you can put x minus y1 over y2.
And then in y3, you could do it, except.
No, it's
Yeah.
two curses.
Think about it.
Wait, oh, that makes sense. Wait.
And then plug in, that might be okay. And then plug in, yeah, you should do that, Albert.
Yeah.
All right, are you getting these answers? So I get for the next guess something terrible. I don't know, you want to store that in your calculator or something? And obviously, this is all about precision, so we don't want to be like saying like, oh, that's about 1.3 or something. We want to actually have that whole value as we go into the next row here. So we have for x2, we're calling it x2, 1.3478261. This number here. Maybe you want to store it. I'll run through this on the calculator too in a second. And then, yeah, and then get your function and derivative value. So what is this? What do we want to call this? It'd be tempting, by the way, if you made this, if you're like all about making this table, make sure you still understand like what's going on. That is called what? What might we use? What symbol might we attach to that? That's x. That's x sub 3, isn't it? Is that clear? At the culmination of each line, we get the guess that goes with the next line. Even if we haven't drawn the next line of the table in here, that is actually x3. And we've done, in total, we've done, x3 iterations. Yeah, Albert.
Why do we start out with 1?
I gave you that guess.
Okay.
Oh, okay, so
Yeah.
we just have to like.
We will usually provide you with the first guess so that like we can all compare answers. But theoretically, you're right. If you're like out in the wild, like you'd have to like look at it or make a guess. A couple of the, I don't know, right? You have to have something to start with though. Was that answer your question too, Peter? Or you good? You had the same question about meeting functions in the wild. Yeah, there are a couple ways we'll tell you. We'll say, sometimes we'll say, I'm trying to think how the instructions given on the homework today. Sometimes we'll say actually do 3 iterations or something, in which case that's pretty clear. Other times we'll say get the 0 of this function accurate to 3 decimal places or something, which means do as many iterations as necessary until it stabilizes, until this doesn't change out of 3 decimals or something like that. All right, and then just down the bottom here, I'm actually plugging this in here, this value, and you can see that in the original question, if you plug this value in we got here, cubed minus this value, it does equal something very close to 1. So just to return to the original question that was asked. You want it better? You can get it better though, right? That's the point. This method allows you to get arbitrarily close values to the actual solution. Yeah, you want it closer, you can get it closer. Just do a couple more iterations. And it converges quickly. If you're actually very interested, if you're like an algorithm person, if you'd like to know how fast these converge, that there is like a whole discussion about the convergence of this kind of algorithm. Depends on what the original function is too, and what your guess is. All right, so then I think already it comes in pretty quick. You're like, okay, I'm using the calculator to do something that my calculator already do quite quickly. It's programmed to do. So like what gives and what are the expectations? So let me make sure that that's clear in our minds too. Clearly this could be asked on a non-calculator question too, right? Obviously we can only maybe ask you to do 2 iterations, or we have to manufacture the problem so that the numbers work out nicely. Which would emulate you if you were living 200 years ago. Like that's what you would have done too. Because you wouldn't have had a calculator. You would have been the calculator. If you're asked to use it on a calculator question, then I'll show you what we mean to do in a second here. What I'll expect the work will show you. We're still expecting that you use this method, but that you kind of record the results of your work as you go, and illustrate that you know what Newton's method is along the way. Yeah.
If the changing thing is a negative, like on the other side?
No, is the answer, but it does. So I think you're asking, like, it seems like we did 3 minus, like at that first example we did the x.
All like on
Yeah, I don't know that the concavity matters as much, but
change which side the tangent is.
I don't think. But I think the thing we wanted that adjusted our guess is the fact that like our new guess was to the, like, so if that tangent line like puts us here and that's our new guess, like if this was 3 and this z value was 0.5, like I think it was for our very first example today on the very first iteration, then we do 3 minus 0.5. Again, I'm assuming that we know this distance here, right? Equals 2.5. But what if, I think this is your question, what if instead, and I think this is the thing, I think you'll find that concavity in the curve actually doesn't matter for new guess. So who cares what the curve looks like here? This is my new guess, right? I'm just saying it doesn't matter what the curve looks like if this is the old guess and this is the new one. Yep, and that's still my new guess though. It's 2.5. Doesn't matter. Oh yeah, I was gonna say the actual thing that matters, and I hear what you're saying, is whether the tangent line goes down this way, right? Because then our old guess was like 3, and our differential is like 0.5. But actually, this distance here, if you calculate it again, it would have been, the slope of this is negative, isn't it? Since the slope is negative, this will come out to be a negative 0.5 when you do the little calculation, right?
But you can just like plug this in.
Yeah, and so then is it still 3 minus this thing? And it will be, right? So all that to say, excuse me, people. Yeah, okay, let me run back to that because I think the picture will help here. I think that's a good question, and I've thought this through myself too. I was like, does this always work geometrically? Seems like algebraically from the warm-up that it always works. So right here, notice we calculated this. How did we get this like z value to be 0.5? Is that what it was, 0.5? Yeah, 0.5. We said this is 3, the slope was 3, and that equals 1.5 over this number. So z is equal to 1.5 over 3, the slope. Well, what if it looked like this instead? Well, then it would come out to be a negative 0.5, wouldn't it? Because the slope is not 3, but negative 3. So that's what I'm trying to explain there, is that then would it still work to do this thing minus this thing? Yeah, because this would be negative, and then it would make it go above 3. Is that, geometrically, does that make sense? Of course, algebraically, with no pictures at all, like Marcus even showed us that just algebraically it always works out to be this formula too. So geometrically it makes sense, algebraically it makes sense. All right, so then what do we ask you to write down when we ask you to do this with a calculator? Let's actually work one through and I'll show you, okay? So on this last example, you guys did this too. Here's what I would do, and I don't know how efficiently you just did that process in your calculator. You're probably like, should I use the home screen? I'm doing y1 on the home screen. No, right? So here's what I would type in. This is like kind of my cheat way, and then I'll show you what I would write for like to make AP graders happy. Okay. So we're going to put the original equation in y1. You probably did that. I'd probably use, well, again, normally people will give you the guess, so you don't have to maybe worry about that. But start by typing this on your home screen. 1 store in x. Try this with me. You're going to love it. You see where this is going? Maybe not. All right, if you haven't already done so, put the derivative in y2. It's the same problem we were just doing, so if it's still there, that's great. And then on your home screen, type in, do you see what I'm about to type in? X minus y1 over y2. And tell me why that actually is the thing, that's the command you want to give your calculator to generate the next guess. And store that in x again. This is like this is how recursion feels. Take your this x, just to be clear, this x and this x are different x's, right? We're taking the result of this calculation and storing it in x, and after that's done, after you type that command in, x will take on a new value, it will be the new guess. And then if you just keep doing that, press enter, 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 it will give you the result of the next iteration. Try it. And it should make sense what you're doing too. Don't just like pretend this is magic. Did it work? I'll do it too on my calculator up here in a second. So here's what I would write though. I would write down the derivative. I would write down the first guess. And then I would write down maybe the showing that I understand Newton's method. That's the thing we want to really see, is that you understand Newton's method along with the result. And then thereafter, I would probably just give the same the results that I got. Demonstrate at least one time somewhere that you know what you're doing and you know Newton's method. And then after that, just like record the results. Okay. Let me see if I can. I'll do this too up here. The original equation was what? X cubed minus x plus 1 minus 1. There we go. All right, so on the home screen, notice I'm not using the graph at all or anything. I'm just going to do one store in x. This is it, right? And then x minus, you can get this in a couple places, but y1. Just so you know, you can type in, actually, if you want, you can type in y1 of x in parentheses, but it'll assume that that's what you mean if huh? Yeah, but I'll clear your calculator so if the type. All right, so 1 was our first guess. Do you remember this? 1.5 was our next guess. And then 1.3, was this what we got? Are those the values we were getting? All right. So do you want a really good approximation? In fact, actually, I've done it a couple times, and even after to 9 decimal place, it's already stabilized, right? Even just after like 3 or 4 times. Well, to your calculator's taste, it is there, right? I mean, it's good enough for your calculator. So that's kind of a slick way to do this, pretty quick. One final word of warning as I send you off. It is possible, you might be thinking like you've just delivered like a message from the gods by giving us this. But this does actually have 2 possible failures. The first is if you're guessing, if you're looking for this root and you make a guess over here, I mean, someone might just be like, you're an idiot. Exactly. Right? It's not always obvious though, because like you might have some curve that like curves weird and the tangent line just happens to hit closer to one root than another that you might have, right? You can imagine that you might not be an idiot, right? It's possible that you actually guess somewhere closer. The other thing that could happen is a failure to converge. So. I think. Oh wait! Don't leave. Sorry, I forgot. The homework is this way. If you need to rip it out of my hands, you can take it back. Sorry, I forgot the whole worksheet. Did you guys get one yet? You all got one? I think I just told one. See you guys.
I know Andrew's gonna buy your